All right. Well, good afternoon, everyone, and welcome to today's Exploring by the Seat of Your Pants event. My name is Joe Gorowski, and I'll be your host for today. We are just getting into October. September is in the rear view. I think we had 30 to 40 live events in September, so it was a jam-packed start to the brand new school year. And October is going to be absolutely crammed full of live events for classrooms. So we've got lots of themes going on, including space exploration. So we'll be talking to astronauts and scientists and engineers, all from the space field, who are helping us look back at our own planet, but also out into our solar system and beyond. So we're really looking forward to seeing how our space exploration month unfolds. So we have a great event in store for everybody this afternoon. We have we're going to be doing Eyes in the Sky. So we're going to spend a little time with Geneviève Gariépy. She leads a team of specialists that support optical space projects ranging from Earth observation to space exploration. She was a systems engineer who helped develop Earth observation instruments, including one designed to measure greenhouse gases from space. She led the Arctic observation mission, measuring greenhouse gases in the northern regions. And her favorite part of her job is that she can combine her passion for optics with environmental values and issues. So let's bring Geneviève in with us live right now. Hey, Geneviève, how are you doing today?
Very good. How are you?
Excellent. It is so good to have you live with us today. Really, you're kicking off our space exploration month as well, so it's pretty cool.
Excellent. Happy to be there.
All right. Well, we have some great classrooms tuning in live via YouTube. We've got Camera Classroom backstage. If you are tuning in via YouTube, don't be shy to say hi. Introduce yourself in the chat. We'll have a Kahoot quiz a little bit later as well, some Q&A action. So it's going to be a busy event. But for now, Geneviève, let's let you take over for a bit.
Yeah, absolutely. Let me just share my screen. It will take a second.
That's okay.
And
I
here
see
we
it.
go.
Perfect. Good to go.
Perfect. Ready to go?
Yeah, looks good.
Excellent. So, welcome everybody. Thanks for being here. So, today I want to talk to you about exploring space. Joe mentioned we can use exploring space to look back at our own planet and to look beyond. Today I will talk about looking back at our own planet. So, I want to talk about how we use space to understand climate change. And before we start, I want to know a little bit what you know about climate change. So this is the Q&A action that's already starting. So in the chat, I want you to tell me, like the classes that are participating, what do you know about climate change? What is it? What are greenhouse gases? What are the main gases that are considered greenhouse gases? How we emit them? So I'm going to wait a little bit. I want to see some information flowing about all of this topic. I want to know what you know.
All right. So there's a slight delay on YouTube, so we should have some answers coming in soon, but we're thinking about the greenhouse gases we know about, what we know about climate change. Ms. Becker's crew, who's joining us, if you have any thoughts on that, if you come up to the camera, I'll bring you in to share some of your thoughts. But let's see what starts coming in via the chat about greenhouse gases and what we know about climate change. Okay, I have a little bit starting to come in via the chat. I have a very simple comment that it's real. So that's one that's coming in. Changing weather patterns is another one that's come in. What else do we have here? I've got some gas examples. I have carbon dioxide. I have carbon monoxide. I have methane are a few examples that came in.
Yeah, those are good. Carbon dioxide is the main one, CO2, and methane is a big one as well, responsible for like 30% of the changing climate. Yeah.
All right.
Really good stuff.
Let's see if anything else comes in. I'll give another couple more seconds.
Okay, but really good things so far. So climate change, you know, you got it right. So it's real, you know, it's been demonstrated. What we want to do is better understand it and better predict it. And it's about the greenhouse gases in our atmosphere that are increasing and then changing the whole climate, which also affects weather patterns.
Yeah, and the only other thing that came in via the chat is someone said it's global. It's happening everywhere.
It is global. That is a very good segue into my next slide. So the next thing I want to show you is is a simulation. I'll just hit pause here just to explain a little bit. This is a simulation that was done by NASA about 10 years ago, and it's based on data from 2006. So this is not real data, it's simulated data. And it shows the quantity of CO2 or carbon dioxide, which is one of the main greenhouse gas in the atmosphere. Okay, so I'm going to let it play a little bit. So the colors that you see here, they're the concentration. So the redder, or like when it goes a little bit purple and even white, it's because there's a lot of CO2 at that place in that time. And the yellow, sort of bluish, it means there's a little bit less. So one of the person in the chat said that it's a global phenomenon, and you can see that it's not only global, it's very dynamic. If you hear about there's 430 ppm of CO2 in the atmosphere, that's a concentration, parts per million. It's not stable. It's not like it's the same amount of CO2 everywhere in the world and it just like slowly increases. It's a very dynamic thing. You can see hotspots like here in Asia, in North America, on the east and the west. You can see hotspots because there's a lot of human emissions of CO2, but it doesn't stay in those places. It goes all around the world because of the wind. So it really travels. So it's a global phenomenon in the sense that if there's emission in one place of CO2, it's not going to stay there. It's going to propagate, it's going to affect the whole world. So that's why it's a global problem that we need to all address together. And you saw before it was very red in the north, and it just became a lot quieter. And we just entered the summer. So we're now in July. So in May, June, it started really going down, the amount of CO2 in the northern hemisphere. And I want to know why. So this is the second part of the Q&A. Do you have ideas as to why there's less carbon dioxide in the atmosphere in the summer?
All right, so we're on the spot again, classrooms. If you have an idea why in the summer there's less CO2, are you asking in the north or in general?
It is in the north. We really saw it happen in the north. I won't play around with my video because it bugged my computer last time, but it was very red in the north and now it's really quiet.
All right, so
And we're gonna
why?
see it's October, it's gonna go back again. It's gonna come back red. It's gonna increase again. So what happens in the summer that affects the quantity of carbon dioxide in the atmosphere?
All right. I kind of want to put a classroom on the spot here. I want to bring Miss Becker's classroom in and see if anybody in that classroom has a guess as to why in the summer there might be less carbon dioxide in the atmosphere in the north. Does anybody have any guess why that might be in Miss Becker's class? Oh, here comes somebody. Oh, can you unmute for us? It's still on mute.
There we go. Is it because of the heat?
Is it because of the heat? No, it's not because of the temperature. Not directly.
All right.
It's a good guess. I can hear some echo now. Sorry. Okay. Yeah, it's an interesting guess because it can affect, the concentration and
So I
the
have
concentration, but it's not the heat.
I have a guess from YouTube.
Yeah.
Is it because less ice coverage and more growth in the Arctic in the summer? More plants.
More plants. Yes, that is the answer. It's not directly related to the ice cover, but it's the more plants. It's because in the summer the trees, they grow leaves again. The photosynthesis goes on. It doesn't go in the winter, and it absorbs the CO2. It absorbs the carbon dioxide from the atmosphere. So that's why people are so like obsessive about planting trees. It's because it really absorbs the carbon dioxide from the atmosphere, and we really see the difference over the summer. So really nice, really quickly guessed. So yeah, so the message here are it's a global phenomenon, a global problem that's very dynamic, and plant trees. Trees really work. So you can see, if you see graphs of concentration of greenhouse gas that goes up with time, it will always fluctuate. There's less in the summer, more in the winter, less in the summer, and then it goes up and up again. So there are many things we can do and need to do for climate change. One of the things that where space is useful and where my work is useful is to better understand all of this, because you see it's very complex. There's so much information, it really changes. I cannot know everything that happens by only doing one measurement at one given place. Like, I'm based in Montreal. If I put a sensor there that tells me the concentration of carbon dioxide, I won't have enough information to understand the whole planet. So when we want to understand the whole planet, it's useful to have satellites, because satellites have a very good view on the whole planet. So they go around the planet in a very short time, and then they cover the whole ground, and then they stay up for like 5-10 years, and then we can just accumulate information. So in my work, I worked on a concept for a satellite, a project that we would like to do, which is called the Arctic Observing Mission. And the goal is to observe what's happening in the north and measure the greenhouse gases in the north, because there's many things that happen. We talked about the trees, we talked about the melting ice. We also have permafrost that is thawing in the north, and it contains a lot of carbon. So when it thaws, it releases a lot of carbon, and then it warms the north, and then it thaws more. So there's like a feedback loop. So we know this is happening. We don't have a good quantification of it. So that's where we need satellites to have good information, so we're able to better understand and then predict climate change, so we're better able to act and mitigate the impact. So my job is basically doing concepts and building satellites. How do we do that? We know where we want to go. We would like, as an objective, to have two satellites that orbit the planet, that gather data over the north and tell us how much carbon dioxide there is. And this is a long-term project. Okay, it takes a lot of time to do that. I cannot just wake up one day and say, "Yeah, tomorrow I'll send a couple of satellites and it's going to work well." I cannot do it alone, and I cannot do it fast. It's a large project. So right now we're working on the concept for this. So it could happen maybe in 10 years, like in mid 2030s. It's a very long-term project, like I said. And there's many steps. So what should I do before sending this there? One of the things that I just worked on is that before sending it in space, we send it a little closer to home. So we can do demonstrations and what we call stratospheric balloons. I'll show you a bit more info about that. Those are like big helium balloons, like birdie balloons, but like giant, like they're 100 meters. And then they bring some instruments that you just built up in the air about 35 kilometers, and then it stays there for like half a day, 12 hours. It gathers data, and then when it comes back, we have information on our instrument, on the science that we're trying to develop. So it's a really good way to test, at lower altitude before sending the real thing into space. So this is a project I worked on a few years back, and it's completed. But even before that, we didn't go straight into the balloon. What we did was we built a first prototype of the instrument uh, in the laboratory, and this is the instrument uh, that for which the goal is to measure the greenhouse gas. So when I was talking about measuring greenhouse gases from space, we need some kind of instrument, some kind of camera with a telescope that will be able to see the CO2 and tell us how much there is. So this was a 3-year project just in itself, just designing this instrument and testing it in the lab. And even before that, since about 2010, there's been studies, there's been like concept, drawings, simulations, just to try and refine what is it exactly that we need to measure, uh, what are the requirements for the instrument, how can it work, how big is it going to be, how much is this going to cost. So this is a very long-term project, and it's very typical of space development project. We always go through phases of concepts, first test, and then some kind of demonstration before we can get into our real objective of sending something into space. And just to give you a bit more info about this one, the demonstration in the stratospheric balloon, how it looks like. So you know, the instrument that we had developed in the lab, it looks like this on the top right. And it's basically, like I said, it's a camera, it's a telescope, but it's, you know, something that's developed specifically to see carbon dioxide. And we mount it on this big, huge thing that we call a gondola. And it goes below that huge balloon that's filled with helium, and that's a launch. So when we let go of the balloon, it looks like this. That's the balloon, and here you can see the instrument that's going to fly off.
It's going up slowly. There you go.
Yeah, and here it goes. So this thing just floats off. It goes all the way up to 35 kilometers, stays there for 12 hours. And then when it comes back, it sort of lands into the woods. So we go in a place where there's very few people. So it doesn't land on like streets and cities and things like that. It lands in the middle of the woods. And then we have a big job of getting this back into our labs afterwards. Okay, so this was the balloon flight that's been done 2 years ago, and we still have our objectives. That's 10 years in the future. So what happens next? What happens in between? So one of the things that we need to do, and that everybody that develops space missions work on, is that we need to make sure that our instruments, our satellite, will survive space. So again, last bit of Q&A here. What I want to know what you think we need to survive. Like, what are the harsh things, the harsh environment that we'll be exposed to as we go into space, as we orbit the Earth? What's different in space than on the Earth that we need to plan for?
All right. We'll put a few more groups on the spot here. What do we need to be thinking about? We take a couple seconds to get the YouTube ones to start coming in. Let's put some pressure on Miss Becker's crew, see if they can guess one or two of them before we take some from YouTube. If anybody has an idea, what we need to play? Oh, there we go.
How are you going to survive space? What do we need to survive space?
We need something that will
Talk about it.
we need something that will follow the Earth's orbit and be protected from the sun's rays.
Yeah, protecting from the sun. That's a very good one. That's what we call in the jargon radiations. So it can be particles, it can be high energy rays from the sun or from elsewhere in space. So radiations is a big thing. We need to protect for it, especially the electronics, like the computers on board. We cannot just like put, a normal laptop or something. It needs to be ready to get bombarded by the rays.
All right, I've got some coming in here via the chat. So temperature, it's going to be very, very, very cold.
Temperature is this one. Yes, it's going to be very cold, and it can get very hot as well. The big thing is that it gets very hot and then very cold as we orbit the Earth, as we're like, really close, bombarded by the sun, and then we're hidden from the sun. So we need to be ready to survive those very high and low temperature, and then the fact that they change all the time as well. Very good.
So Geneviève, I'm not sure why. Maybe it's something to do with the connection, but it's a little bit challenging to hear your microphone right now.
Oh no, was it
And a little bit robotic. So I think the one way that we might be able to fix it, if you want to exit and come back in right away into the call.
Oh yeah, I'll try that. Okay. I'm gonna.
Okay, so hopefully when Geneviève comes back in, it'll clear up whatever's going on with the microphone, but she was sounding really, really robotic. So hopefully when she comes back in, we'll get to hear her nice and clearly, and we'll continue with today's lesson. In the meantime, we will be having a Kahoot in just a moment, so I will share the link It's kahoot.it, and then it's going to ask you for a PIN number, and that is
Oh boy.
okay. I think we got you back, Genevieve.
Am I?
Yeah,
Okay, good.
it sounds really good now too. So
Excellent.
that's good.
I got scared a little there. Perfect.
No, it's technology. I don't think it matters where you are in
Yeah.
the world. Sometimes things just kind of blink out.
Yeah, perfect. All right, so let's go back. We had temperature, we had radiation.
Yeah,
Do we see my screen? Yes. Okay,
yeah.
perfect.
And I had one more in the chat. Just they were saying like lack of gases or lack of oxygen was another
Lack
one.
of gases. Yes, that's very good. Again, in the jargon, it's called vacuum. So,
Uh-huh.
yeah, there's just no
Uh,
atmosphere, there's nothing. Yeah.
all right, that's what I have coming in the chat so far.
Very good. The only one missing, and it's a bit of a cheat. It's not when you're in space, but it's getting into space. You're gonna get exposed to a lot of vibrations. So during the launch, you're gonna get shaken up, basically. So just a few notes on that before we conclude. So if you haven't seen a launch before, I have a little video to show you how it's not necessarily very smooth. And here on the right, it's a picture of one of the satellites that comes from Canada. Actually, there's a company called GHG Sat based in Montreal that do satellites for greenhouse gas, and it's a very tiny satellite. It's like big like this. It's big like a toaster, like a big toaster. Uh, and you can see here at the top, it's this little tiny one. So when we send a rocket like this, there's like actually a bunch of satellites. We can send like hundreds at the same time. And they're on top here. So here you can see those are other ones like from SpaceX. So it's basically a ride share. It's actually called a ride share. And when it gets up, so I'm just gonna play this little video. It's yeah, it's not smooth. It's gonna shake a lot. So this is quite intense, and we need to make sure that it survives this launch. We need to make sure that when it gets into space, all the screws are still there, and everything is still in place. So what we do for that, we always have like a team of engineers and designers that will design and like simulate the system to make sure that it will survive vibration. But it's not enough to just do analysis and design. We also need to do testing, and we do this for vibrations, but we do it for temperature and vacuum and radiation. But for vibration, it looks like this. So this is actually again the satellite, but not in its full form. It's this one, and we put it on a table and we basically shake it as it will be during the launch. So this is quite intense. It's always, it's a week of tests, and all the mechanical engineers are stressed out during that week because it can break. And actually, that's why we do it. We test it because if it's gonna break, we want it to break on Earth, so we know how to change the design and then fix the problem. We don't want this to break during the launch and then not work in space. So that's one of the reasons why there's so many steps in what we do when we develop and launch satellites. Whoops, sorry. So here you have a view of the complete life cycle of a satellite. We just talked about the launch. Of course, that's an important part. we talked a bit about the design and the build. So we always start with the design. What do we need the satellite to do? What kind of instruments we're going to put there? And then we build it. And we don't build it just one. We build like a prototype in the lab, one that's going to go on a balloon, one's that's going to be shaken up. That's not the one that goes in space. This is just like the test one. One that will put on very low and high temperature. So there's many different versions that we build. And then once we launch it, we operate it for like 5-10 years, which is the average lifetime of a satellite. And then we decommission it. So that's basically handle the end of life. So we want to make sure it doesn't just, stay in space forever. We want to try and like bring it back into the atmosphere so it doesn't become like a debris in space. So within all of this is a question I'm going to leave you with for the day. So I've explained how we can use satellites to better understand climate change and to use it as a tool to better manage our planet and, have a positive impact on the environment. But of course, as we do this, every step has an impact on the environment. And it's a big question and it's an interesting question to try and think how we could maybe improve this. And this is something we actually need your help and figuring out. There's a lot of people working on this and will be working on this for many years to come as well. And CSA has just launched a space brain hack. So we basically want teams, it can be within your school, it can be student clubs. We want you to think about maybe one of these steps. Look a bit into it, how we, what we do, what kind of material we use, what kind of processes we use, and think about how we could maybe improve these processes to reduce the environmental impact of a satellite. So if you're interested in this challenge, you can look it up. It's called the Space Brain Hack, and you have a QR code there as well for teachers if you're interested in getting the information. And we want ideas before February, so you have a couple of months to think about this.
All right. Geneviève, thank you for that great presentation. I think we sometimes forget that part of space exploration is looking back at our planet, learning things about it that we could not see or understand from the ground. So you get to really think about cool problems and the solutions so we can understand what we're seeing and the changes that our planet is undergoing.
Yeah.
All right, so we'll take that presentation out and we're going to play a little Kahoot with our classes that are joining us today. So I'm going to share my screen. Make sure I pick the right screen. There we go. Okay, so you need to head to kahoot.it. At kahoot.it, then your PIN number for today is going to be 704050. If your class happens to have one-to-one tech at your seat, maybe Chromebooks or tablets, you could join that way. If not, no big deal. Your teacher can pop it up at the front of the room and you can shout out your answers to him or her. So we'll give a couple seconds to get a few classroom groups loaded in here with us. And then we'll go live and we'll see who comes out on top for today.
I love those names.
Yeah, they're auto-generated, but they're pretty cool animal names, like the green yak, the melodic rabbit, the smiling camel. So we have some nice auto-generated animal names coming our way today. So Geneviève, while we wait another minute or two for a few more classes to join, do you have any projects that are close to completion right now? Is there anything you're working on that might be launching soon? Are you in a testing phase of something right now? What's going on?
Launching soon. It's a good question. Launching soon. We have, I think the ones that we're involved in that's the closest to launch is for quantum communication. So this in a minute, it's a bit complicated, but we basically want to communicate between the ground and space in a way that's very secure. And then quantum technologies can help us do that. So that's going to be a first from Canada to
now, is that
to do that?
Like, obviously it's complicated, but is that kind of roughly communicating with light?
Yes, it's communicating with light, and it's like a very special form of light with very specific properties. If you heard of entanglement before, sometimes it's in sci-fi movies talking about entanglement, and that's what we use there.
All right.
for enhanced security.
Very cool. Let us play some Kahoot. So remember, the quicker you get the right answer in, the more points you are in fact going to get. So here we go. Counting down. Our first question is a multiple choice. Which is the main greenhouse gas in the atmosphere? We have nitrous oxide, we've got carbon dioxide, we've got hydrofluorocarbons, or methane. So let's get our answers locked in there. You have 20 seconds for each question. Remember, the quicker you get the right answer in, the more points you're going to get in the end. All right. Good job, crew. Good starts. Let's take a look at our leaderboard. The charming bear is holding down that top spot. Let's go to our next question. A little true and false action coming your way. There's more carbon dioxide in the summer in Arctic regions. Is that true or is that false? More carbon dioxide in the atmosphere in Arctic regions in the summer. True or false? Got a few more seconds to lock in that answer. And then we'll, oh, yeah, good job, crew. That is false. I think, Geneviève, that's such a good demonstration of how impactful plants can be. And in the Arctic, they're not your, the really big trees in places like the rainforest, other places around the world. It's a lot of kind of grasses and shrubs and things like that.
Yep. It still has a huge impact. Yeah.
Absolutely. All right, Green Yak holding down that top spot. We've got another true and false coming your way. Melting permafrost releases carbon dioxide into in the Arctic. Is that true or is that false? Melting permafrost releases carbon dioxide in the Arctic. Got about 9 more seconds to lock in your answers, and then we'll take a look at our leaderboard one more time. All right, that is true. It also does something I read recently. They call it drunken trees because some of the trees that are in the permafrost start to lean at really funny angles or even fall over as the permafrost begins to melt. Charming Bear taking the lead again. Here is our last question. What needs to be considered when building a satellite? Do you have to think about temperature? Do you have to think about vibrations? Do you have to think about radiation? Or do you have to think about all of the above? You've got a few more seconds to lock in that final answer. We'll take a look at the podium, and then we will finish off today with a whole bunch of Q&A action to wrap things up. All right, all of the above is absolutely correct. Let's take a look at our podium. In third place, we've got the eager pigeon. In second place, the melodic rabbit. And holding down that top spot, all the bragging rights go to the green yak. All right, crew, thanks for playing along today. Let's shut that down. And let's switch gears. Let's do a little Q&A as we get ready to wrap up today's lesson. So, Geneviève, I'm going to start with a question here from YouTube, and then I'm going to grab Ms. Becker's crew in here to see if we have a few questions from them. But we'll start with a YouTube question. And this question's about launches. Launches are a very tricky time. Have you ever been part of a project or know somebody who was part of a project that didn't make it to space?
Yes. Yeah. I do know people. So sometimes it doesn't get to space because we never get to the launch. That happens, and that projects are canceled or they're just gonna go through because it costs a lot of money. So, that's why as well we do all the studies at the beginning to make sure that what we do will be useful and is right and costs the right amount of money. So sometimes it just doesn't make it. That happens to me all the time. But I like, developing projects and thinking new ideas, and it's okay if they don't all make it.
Yep.
And sometimes it doesn't work at the launch. That's always very heartbreaking. I know one person to which it happened, and it's part of the job. And then we're closer to a real launch when we got all the way there, and then it just fails at launch because of the rocket. Then at least we got all the development done, and then it's easier for the next one.
All right, I'm going to bring in Ms. Becker's crew. Let's see if they have a few questions for us today. Here comes somebody.
What made you want to do your job?
That's a good question. Can you mute? Oh yeah, okay, perfect. Actually, I I never dreamt of like working in space. A lot of people I work with at the Canadian Space Agency, it was like their dream when they were kids. I didn't really know what I wanted to do. I really liked like physics and mathematics when I was in high school. And then I got really into optics. As we said in my bio, I really love optics. And later, so that's what I did because it was just so much fun. It's really cool experiments. Like the theory is like simple but elegant. You can understand very well stuff when you're in optics. And then later on, I discovered that you can use optics for the benefit of the planet, for Earth observation, and that's what really got me hooked into the space sector. It's the impact I could have using the fun optics knowledge I had.
All right. We'll see if Miss Becker's class has another one before we go back to YouTube.
Okay.
Have you ever like thought have you ever built something to launch?
Have I ever
Have I ever put the
Built something to launch.
Oh,
launch?
build something.
Oh, it's something to Okay. That's okay. No, wait.
No, not myself. I like I said, I always like work on the projects that are like early development. That's kind of what I like to do. So I never went to a launch and didn't participate to something that's already been launched. I'm still early in my career, and it takes, you saw it can take like 10, 20 years. So I think if we talk back in 10 years, the answer will be yes. But for now, I really like more involved in the early development.
All right. Let's grab a couple questions from YouTube. We'll check Miss Becker's class one more time as well. Do you think there'll be a way to refuel or repair satellites in orbit?
Refuel or repair? I won't say no to this because who knows what we'll be able to do and what you'll be able to accomplish once you're among us working in these cool projects. It's been known to happen. Like I think the Hubble satellite, if you want to look it up, has been repaired in space because it was a very important one, but it's cost so much money. So right now, that's the limitation. It's how much it costs. So if we want to do that, then in a sustainable way, we just need to figure out like an effective way to do it.
All right. Another question. So we talked about a satellite that can look at greenhouse gases. What else can satellites be used to observe on Earth?
So many things, so many things. One of the things that you probably use all the time is a GPS. So GPS work on satellites. So if you're on your phone and you want to know where to go, where you are, that's some satellites working for you. Uh, it can be very useful. We have a project at CSA that is due to launch in a couple of years for wildfires. So that's another thing that's really important, for our planet, for climate change, is to be able to detect which wildfires are the most dangerous, that are likely to cause the most damage, so we can all put our resources there. And satellites can be useful because we have such a huge territory in Canada. There's just so much to cover that satellites are the way to do it because then we can see everything and then pass over a couple times a day and see what's happening with the fires.
All right. Very cool. We got some great questions coming in via YouTube. So this one is actually one that I thought about because I was just in the Canadian Rockies for a few days, doing some camping on a little expedition, and I've never seen so many satellites going by. Like almost every time I looked up, there'd be several. So when designing a satellite, are there things that can be done to help preserve that kind of night sky view?
Yes. So remember when I talked about the complete life cycle of the satellite? The last one was decommissioning. And that's an important one and one that we put more and more focus on. Because if we don't do anything, the satellite will just stay there. So it's not just the number of active satellite, it's the number just of stuff that stays in space. So we need to really think about when the satellite useful life is over, how to bring it back down, how to get it out, of the space because it affects the night sky. It also affects the safety of satellites and of humans that are in orbit, that having so much stuff that can collide together. So that's another tricky problem, but interesting problem for you and the next generation that's going to come and work with us.
All right. Let's bring Miss Becker's crew back in. I think I see someone coming up to the camera.
what did you do in this job?
What do I do in my job?
Yes.
Oh my God. That's a tricky question again because my job varies so much. You know, a typical question is like what one day looks like, and my job varies every day. So, and it varies through the years as well. So at the beginning, when I started working on satellites, I was working a lot in the lab, with the instruments that I showed you. So I was the person who was responsible for the team that sent the instrument in the stratospheric balloon. So I do a lot of calculation. I do simulations, on my computer to try and predict how the instrument is going to behave. And then I take the data, I analyze it, see if it behaves like I thought. If it does, then I'm happy. If it doesn't, I try to figure out why. And then I have a lot of meetings in my job as well. I do a lot of teamwork. Just like I said, nobody can wake up one day and alone send a satellite. We need a lot of people working together. So that's a typical thing of my job. So I think like the two things that I always do, and that throughout my career are always true. I work with teams. I work with other people that have other expertise than mine, and I solve problems. I'm a problem solver. That's what an engineer does, and that's what I like to do.
All right, very cool. Well, Geneviève, thank you so much for a great event today. It was really great to kind of peer into your world, the work you get to do, the projects you get to work on, the cool people you get to work with. I'm going to share this link here. It's really big, but I think the best way to search Space Brain Hack, it'll come up there as well, or CSA Space Brain Hack, and you'll be able to find it, which is pretty cool. Yeah, I guess maybe just as we're wrapping up, Geneviève, if you have any advice for somebody who might be interested in a space career, any advice for students, what they should be doing now?
Go for it is my advice. Is be confident and just follow what interests you, what looks fun to do. The Space Brain Hack is a good example to get into that mode of thinking, solving problems, and then as you go through your study, just keep doing what you find interesting, and I'm sure you'll find a career that's going to be very fun and fulfilling.
All right. Well, huge shout out to our classrooms on YouTube who tuned in. Thanks for playing Kahoot. Thanks for sending in some great questions. Thanks to our camera crew. And Geneviève, it was a real pleasure to host you today. Thanks for kicking off our Space Exploration Month.
Thank you so much.
All right. We'll hope to see everybody else as October continues. But for now, thanks so much, everyone. Great to hang out with you.